Okay, guys, what we're going to go over today is we're going to start the second half of this unit. Okay, I say second half, it's more like the last third. Okay, so the last third of this unit is about gravitation, okay, and circles. Right? Because obviously the force of gravity can act as a centripetal force. Right? We see that in tons of things in nature. Okay, the fact that the Earth orbits the sun, okay, in a circle, the Moon orbits the Earth in a circle. Okay, that planets are spherical. By the way, Earth is round. Okay, it's not flat. If you think it's flat, the door is right there. You can go drop my class right now because you're just wrong. Okay, it's just bad for you. Okay, but yeah, we see that circles, okay, are simply a shape that happens a lot, and it happens a lot because of gravity. Now, why is it that Earth orbits the sun and not the other way around? By the way, it's not the other way around. Okay? Yeah, the sun is bigger. Okay? In actual fact, the Earth doesn't orbit the sun. The Earth and the sun orbit a common center of gravity, which lies like this far from the center of the sun because the sun is so big. Okay?
What if the Earth's a cylinder?
But it's not. Okay? We know because we have pictures of it. And those pictures aren't fake. See, they got an argument for everything. Okay? So, the moon and the Earth, okay, like we always picture that the moon orbits the Earth. Because for all intents and purposes, it does. But it actually doesn't orbit the center of the Earth. The Earth and the moon actually orbit a point that's about 10 kilometers below the Earth's surface. Okay? So the Earth actually wobbles back and forth while trying to orbit this center of gravity between the Earth and the moon. Okay? But they orbit each other because they both have mass. Okay? Mass is what determines how much gravitational attractive force there is between two objects. Okay? So gravity, even though we talk about it like this all the time, gravity is not the force of one thing on another. Okay? Like up to this point, we've always said everything falls towards the Earth because it's attracted to the Earth. And it makes it seem like the force of gravity comes from the Earth and everything moves to the Earth because of the Earth. But in actual fact, Newton's experiment, story with the apple falling and hitting him in the head, okay, the apple and the Earth are attracted to each other. Okay? The Earth is just as attracted to the apple as the apple is to the Earth. But the Earth is huge by comparison. Okay? So we don't notice the Earth accelerating towards the apple. They're actually accelerating towards each other. But because of the apple's smaller mass, it doesn't look that way. Okay? Does everyone kind of follow me there? Okay, so right now is where you want to be thankful you're not in Mr. Dickey's class. Okay? Because he does something when he teaches this lesson that makes people feel very uncomfortable. Okay? He makes you look at a person next to you right in the eyes and say, I'm attracted to you. Okay? Yeah, and it's really awkward. People get very uncomfortable, okay? And you should, because that's just a little weird, okay? But the weird thing is that it's also true, not in the sense that makes you uncomfortable, okay, but in the sense that you both have mass, okay? And because you both have mass, you both have the ability to attract things to you by gravity. You just have so little mass that your ability to attract things towards yourself by gravity is basically completely ineffective when you're standing where? On Earth, because Earth just overwhelms everything around it. Okay? Now, if you were out in interstellar space, a long way from any other mass, could you attract things towards you by gravity? You could. But you probably still wouldn't. Okay? Simply because you have so little mass. Okay? You have so little mass that even a little mote of dust, okay, floating through space would not move towards you by gravitational attraction. It might move towards you because of static. Okay? If it's positively charged and you're negatively charged, it'll move towards you. Okay? Because actually, those other field forces, gravity and magnetism, are actually far stronger than gravitational attraction. they get obliterated by gravity because gravity is dependent on mass. And there's a lot of mass out there. Okay? So usually we don't notice electrostatic and magnetic forces as much because gravity is always more, simply because there's so much mass around. Okay? Everybody kind of with me there? All right. So this is what Newton thought up, but could never make work. Okay? Newton's given a lot of credit for things that he actually doesn't fully do himself. All right? And it's because of the time he lived in. He wasn't able to run a lot of the experiments that he would have liked to run because the technology wasn't available. So Newton started running thought experiments, okay, where he envisioned experiments in his mind and then, yeah, came up with the results. It seems like kind of a cop-out, but that's what he did, okay? And some of these thought experiments are the basis for things other people proved for him later. But because they were his idea, he gets credit for them. All right? And one of those things was this idea of gravitational attraction. Okay? He said that the force of gravity is dependent on three things. Okay? The mass of the two objects and how far apart they are. Okay? Now, the mass affects the force of gravity linearly. If you double one of the masses, you're suddenly going to have twice as much gravitational attractive force. Okay? The other part is what we call their separation distance. We put r in there because it's like a radius if it's in orbit. Okay? That is the center to center distance between the two bodies that are attracted to each other. Okay? But that's squared. So that means then that the farther away two objects are, they are exponentially less attracted to each other. Okay? Now, again, don't try and put this on sociological things, like that means long distance relationships will never work because if you're far apart you'll be exponentially less attracted to each other. It doesn't mean that at all, okay? You can totally make things like that work in real life, okay? But in terms of gravitational attraction, the farther apart two objects are, the less attracted to each other they will be exponentially, okay? So that means that they will exert less attractive force on each other. Everyone all right with that idea? Okay. So that was Newton's idea. Mathematically, it never worked. He got numbers that were enormous, that would have crushed the things he was studying. Okay? What he was missing was a special number. Okay? That special number is the gravitational constant, the universal gravitational constant. On your formula sheet on the back, under other useful constants, oddly enough, is this number, 6.67 times 10 to the minus 11 Newton per kilogram squared, or something. I can't remember what the units are. I never remember what the units are. What the units are. Newton meter squared per kilogram squared. Okay? That's the number that makes his idea work. He never discovered it. Okay? The reason being is it's really hard to run an experiment about gravitational attraction between two masses close to the Earth. Because what does Earth do? It just messes with them, right? They're attracted to the Earth. It's an overwhelming force. Okay? It wasn't until a guy named Cavendish came along who developed an experiment that essentially put gravity perpendicular to the experiment and then was able to make it work. I'll show you somebody replicating his experiment at some point today. Okay, so this is Newton's idea. Force of gravity is dependent on these two things, but it's actually also dependent on big G. That's the 6.67 times 10 to the minus 11 number. Okay, having a number like that, that's 10 to the minus 11, eliminates that whole crushing gravitational force problem that Newton experienced, because now he's multiplying by this tiny number. Okay, so according to this then, Okay, if the masses get bigger, the gravitational attractive force gets bigger. The distance gets smaller, the gravitational attractive force gets exponentially smaller. Okay, so if you kept eating and eating and eating, would food eventually come to you? Theoretically. I mean, practically, no. You'd have to be close to the mass of the Earth before any noticeable difference would happen. Okay, but theoretically, I mean, stuff comes to the Earth all the time. Okay, it gets attracted to the Earth by gravity and burns up in the atmosphere, and things like that. Okay. All right. So, for an object to have weight, force of gravity, it has to interact with another object. We have weight because of our interaction with Earth. Okay? But here's something weird. I don't weigh the same amount everywhere on Earth. Why is that?
Gravity is different.
The acceleration due to gravity, yeah, it's different, but why?
The Earth's not perfectly spherical.
The Earth's not perfectly spherical. It's also not flat, because that's crazy talk, okay? But it's also not perfectly round, right? And the reason for that is how the Earth formed, okay? It formed because it was a conglomerate of a whole bunch of rocks that hit each other in space, and it was molten, and it was spinning really fast, okay? And the fact that it was spinning really fast causes it to flatten a little bit, because at the equator, it would be spinning really fast, but at the poles, hardly at all, right? Because it's just doing this at the poles, right? So because of that, there's this like angular momentum thing that would have caused some of the mass to go out a little more at the equator, and so Earth is wider than it is tall. So where do I weigh more? At the equator or at the North Pole?
North Pole.
North Pole. I'm closer to the center of the Earth at the North Pole because Earth is squashed a little bit. Okay? I weigh less twinkling my toes in the sand on the beach at sea level at the equator than I do standing on the highest point on the Earth's surface. I'm actually heavier on top of Mount Everest, the highest point you can stand on Earth, than I am at sea level at the equator. That's how not round Earth is. Okay? It's that much wider at the equator than it is even, I mean, Mount Everest is not at the pole, it's like halfway. Okay, that sort of makes sense? So the further away you get from the center of the Earth, the less you weigh. If you actually look at this, there's a person who did a statistical study. More Olympic records are broken near the equator than they are further away. Okay? When they hosted the Olympics in 1968 in Mexico City, they broke a whole bunch of records because it was close to the equator, but also at a high altitude. Okay? There was like the least amount of gravity there had ever been, okay, for an Olympic Games. Okay? And when we're talking about highly tuned Olympic athletes, every little factor counts. Okay? Because I mean, you're breaking, a shot put record by 1 centimeter. Well, if you got a little lower gravity on that day, maybe it's your day. Okay. Making sense? Okay. So, if I'm standing, at sea level, at the equator, a 70 kilogram person would weigh 684.6 newtons. Okay? If I go to the North Pole, 4 newtons more. Because I'm that much closer to it. Now, 4 newtons, are you really going to notice that? Not really. I mean, you're not going to notice 4 kilograms or 4 newtons out of 680. But it's there. Okay? If you go to Chicago, which is about, let's say latitude-wise, maybe about here, 686.2. So you weigh more in Chicago than you do, at the equator, right? You go to the top of Mount Everest, 685. You still weigh more at that point than you do at sea level at the equator, right? If you go to low Earth orbit, you weigh 647 newtons. Does that seem strange? Didn't we just watch a bunch of videos last week of Chris Hadfield weighing nothing? When you're on the International Space Station, are you weightless or are you apparently weightless? You're apparently weightless. If you were really weightless, you wouldn't stay in orbit. You'd fly off, right? You still have a gravitational attraction to the Earth. You just can't stand on the scale and measure it at that point, okay? Because to be on a space station orbiting the Earth, you're actually always falling. I'll talk about that one tomorrow when we talk about satellite motion, okay? But you're only apparently weightless when you're in low Earth orbit, right? But you still have a fair amount of weight. 647 newtons is still considerable, right? If you go to high Earth orbit, where all of our global positioning satellites would be, you're quite a bit further away. And now you only weigh 15.5 newtons, because the relationship with separation distance is exponential, inversely exponential. So the bigger it gets, the exponentially less you would weigh. Okay, so this would be low Earth orbit right here. High Earth orbit would be way out there. And even if you were out where the moon is, you would still be attracted to the Earth. Not very much, but you still would be. Okay? And if you went to the outer edge of the solar system, you still would have some gravitational attraction to the Earth. But your gravitational attraction to other things might be greater because they're closer or bigger. Yeah. I'd say at the edge of the solar system, your weight would more be due to the sun than it would be to the Earth. Okay? Even though you're further from the sun, okay, you would still be more attracted to it because it's so big. Right? So that said then, how come I don't fly towards the sun on the Earth's surface? Don't I have some gravitational attraction toward the sun standing right here? I do, but what's closer? Earth, and that makes a big difference. Remember that our relationship is exponential. I'm exponentially closer to the Earth than I am to the sun, so I'm way more attracted to the Earth than I am to the sun. Okay. All right, is that also why the moon stays in orbit? It is. Okay? The moon is way closer to the Earth than it is to the sun, so it doesn't fly off. It's attracted to the Earth more than the sun. All right. Everyone okay with that idea? Okay, so Newton studied those attractive forces, and like you said, he came up with the relationship. He was right about the relationship between mass and gravity and radius and gravity, but he was missing that special number of big G. Okay? So any two masses will be gravitationally attracted to each other, okay, based on how big they are, linearly, and how far apart they are, exponentially. Okay? Everybody all right with that?
What would happen if an object had, like, there's no gravitational attraction acting on it?
So there was nothing anywhere near it?
Let's say we have like a closed system, like entire, like
Isolated, completely isolated system?
completely isolated, like different universe, like, I don't know.
Then it would travel, if it was moving, it would travel in a straight line.
Oh, so there's like nothing then?
Yeah, it's just
That
Newton's
makes
first
sense.
law, right?
Yeah.
There'd be no net force. Okay? The reason something orbits something else is because gravity's acting as a net force and making it fall in. Right? Okay, so to make this formula work, okay, an experiment was devised by a guy named Cavendish. It wasn't this high tech, but it effectively amounted to this, and I'm going to show you a video of a guy replicating it here in a minute. Okay, but he realized that nobody could do an experiment between two masses within the Earth's gravitational field unless there was a way to eliminate Earth's gravity from the experiment. Well, the way to eliminate Earth's gravity from the experiment is to make it perpendicular to the attractive force between the two objects you're studying. So you make the attractive force between the two objects horizontal because gravity is vertical. Okay? So now you eliminate it. Now, that's all well and good, but then you've got to have some way to measure the amount of force between these two objects. Right? So what Cavendish, the guy who came up with this, came up with was what we call a torsion balance. So it uses torque to measure force. Okay? Torque is a twisting force. Okay? So what he did is he had a bar that had big lead spheres on it. So they'd have been really heavy. Okay? And those didn't move. Okay? They were stationary on this bar. And then he had a little torsion fiber, so like a little wire, okay? And all wires have, as a physical property, okay, a torsion kind of ratio, like how much force it takes to twist them X number of degrees, okay? It's a metallic property, right? So he had this wire, right? And he knew how much torque it would take to turn it or twist it a certain number of degrees. And then, on the end of that wire, he had two small spheres, probably like, I mean, it wouldn't have been styrofoam, but it would have been something light, okay, like pith or something like that, something very light, right? And what he did is he set these up so that they were apart, okay? Since gravity has been eliminated from Earth, the only force that should be causing the small ball to move towards the big ball is gravity. He made sure he used things that wouldn't carry an electrostatic force, so there'd be no, electrical force there, no magnetic force there, okay, because it's lead, right? So it's not steel or iron that would possibly make a magnetic field. The only reason for them to move together is because they're gravitationally attracted to each other, right? So he sets this up, and then he measures the angle, the change in angle of this bar, okay? And over time, it twists because the small ones start to move towards the big ones, right? He just measures the angle that it moves, and then from there, he calculates the force of gravity between those two masses. That was what Newton couldn't measure, okay? So even though Newton knew this was true, he was never able to run an experiment where he could measure that value, because Earth's gravity always got in the way, right? So Cavendish's experiment allowed him to use the torsion, okay, to measure how much attractive force there was, and then from there, he could calculate the missing number, right? He could calculate that thing that Newton never had, the universal gravitational constant, okay? The missing number in that experiment, okay? Everybody all right with that idea? So it was actually a pretty ingenious experiment, and when it comes right down to it, actually quite simple too. All right, so I'm going to show you a video of a guy who replicated this with some bowling balls. All right, and then the graph we've got up here on this slide here is simply showing us that relationship between the force of gravity and separation distance, okay? We've got a curve that is getting exponentially smaller, right? So as r gets bigger, the force of gravity is getting exponentially smaller, the opposite of what we saw in the video where r was getting smaller and fg was getting exponentially bigger. Okay, questions on that? Everybody okay with that idea? All right, so let's try one of Newton's calculations here, okay, using his force of gravity formula. Up until now, we've always just calculated force of gravity by doing this. Okay? That's fine as long as you have what? As long as you have little g. But little g isn't the same everywhere. Okay? That's the advantage of this formula. It essentially eliminates little g. Okay? Or figures out exactly what it is, okay, for each different location. So let's say we're taking an object to the moon, okay, and we want to figure out what its weight will be on the moon, right? We know its mass, 0.65 kilograms. We know the mass of the moon, 7.36 times 10 to the 22 kilograms. And we know the radius of the moon. If we're standing on the surface with this melon, that's going to be how far the melon is from the center of the moon. Agreed? Is that an okay assumption? All right. So if I'm plugging in my numbers here, I'm going to plug in the gravitational constant, 6.67 times 10 to the minus 11, times the mass of the moon. Okay, so that's 7.36 times 10 to the 22, and the mass of the melon, 0.65 kilograms. Then I'm going to divide that by the radius of the moon squared. What do you suppose people forget when they're using this formula? They forget to square radius. Most common mistake. If you forget to square radius, should your mistake be obvious? Yeah, because your answer will be ridiculously large. Yeah, okay, because you have multiplied or divided by a number that was way too small. Okay, all right, so if we punch all that in now, this being punched into your calculator does require you to be a little extra careful because you're going to have a lot of brackets here. Right? So first I got to put in the universal gravitational constant. So I'm actually going to have two sets of brackets, 6.67 E negative 11. I'm going to close that bracket. Put in the mass of the moon, 7.36 E 22. Close that up. Put in the mass of the melon, 0.65, and then close the top. Okay, so now I've got all of the top there, okay, and then I'm going to divide that by the bottom. So in brackets, 1.74, E6, close the brackets, square that number. Okay, so the mass of that melon on the moon is 1.1, or actually, yeah, we only have two significant digits there, 1.1 newtons. Okay, everybody all right with that formula? You will be required to manipulate it a little bit as well from time to time, but it's just algebra. Is that a lot lighter than the melon would be if it was on Earth? Yeah, because on Earth, okay, it would be 6.3 or 6.4 newtons, okay? 6 times heavier. Okay. So on the moon, you weigh 1/6 of what you do here. Right? Why is that? Why do you weigh less on the moon? It's a lot smaller mass. Okay? It's actually also radius smaller, but that should actually do what for your case? Should help it, right? If you'd always be closer to the center of the moon than you are to the center of the Earth standing on its surface. But the moon is so much lighter than Earth. Okay? All right. Everyone all right with that idea? So moon is a lot smaller, moon is a lot lighter. Okay? But our moon is actually quite large. Compared to, let's say, other moons and their parent planets. Okay? If you look at, like, Jupiter's moons, some of Jupiter's moons are larger than our moon, but Jupiter is also a lot bigger. Okay? When it comes right down to it, the ratio of the moon's mass to the Earth's mass is quite close. Okay? It's more of a double planet than it is a satellite and a planet. Okay? So the moon is very big. Okay, for at least a planet of this size. Okay. Does that have important effects for us? Yeah. Okay, like tons of really important effects actually. The main one that we see are tides. Yeah, causes the tides, right? The ocean is attracted to the moon. Okay, so you get high tides and low tides. But believe it or not, it actually affects the tilt of the Earth, the rotation of the Earth, okay, the length of a day. Okay, all of that stuff is actually affected by the moon's gravitational effect on the Earth. Okay? Without the moon, things would be a lot different. Did the moon used to be closer?
Yes.
Yes, a lot closer. Okay? Would that have made Earth very different? Yeah, a lot different. I mean, imagine what tides would be like if the moon was a lot closer. Right? Like right now, it takes the moon 28 days to orbit the Earth. Okay? By our estimates and calculations, there was a time where the moon orbited the Earth more than once a day. Imagine how close it would have been then. Okay? Tides would have been like if you had a bucket full of water and you just violently shook it back and forth. Okay? The tides would have gone everywhere, okay? Being that close to the Earth. Yeah? So that's what we just did there. Now, gravity, obviously, acts as a centripetal force. Okay, we see that all the time. Okay, even in like vertical circular motion, okay, we see that gravity can act as a centripetal force. So here's how that works. To your point, Callum, earlier you had asked what would happen if you had a completely isolated system. The answer is, if I had this mass here and this mass here, and they had zero gravitational attraction, then this mass would just travel in a straight line according to Newton's first law. Right? The reality is that there is a gravitational attractive force, and it has to pull the objects together. That is center to center. So that object tries to fly by the Earth, but it's attracted to the Earth by gravity. That doesn't really change its speed, it changes its velocity. Okay? So it still tries to do this, still tries to go in a straight line, but it's attracted to the Earth. Okay? And it keeps doing this thing. If I go all the way around here, what shape does it make? Right. Okay. That means if something is orbiting something else, gravity is acting as the centripetal force. It also means that that orbiting object is always accelerating towards the Earth. In other words, it's always, well, not necessarily getting closer, but it's always falling. That's why on the International Space Station, you're apparently weightless. Like, if you're falling, do you feel your weight? No, not until you hit the ground. That's bad. Okay? So if you're on the International Space Station, you're always falling. The International Space Station is always falling. So you're actually apparently weightless, not actually weightless.
Do you feel more nauseous or sick because of that?
Astronauts, when they first go into zero gravity, zero gravity, okay, feel nauseous, yeah, for the first few days, but there's a very rigorous selection process that goes on. They don't have too many pukers, okay, because that selection process eliminates people like me that would vomit, okay. So yeah, you're always falling, okay, and that's what creates that orbital thing. We've got that centripetal force, a net force directed center to center, okay, that's going to cause an acceleration towards the center and cause that circular pattern that we see in orbits to form. Okay. Let's see if we can use this idea to calculate how fast the moon moves in its orbit. Okay, so the force of gravity acts as what kind of a force for the moon? A centripetal force. The moon moves in a circle around the Earth. Okay, so I can say then that the force of gravity is the centripetal force. But I'm not going to use this. Why not? I have no idea what G is out where the moon is. Okay? It's definitely not 9.81 way out there. All right, so I'm not going to use that. Okay? I'm going to use this. So mass of the Earth, mass of the moon, over r squared equals centripetal force. What radius should I use? R is always the distance from center to center. This is where you're going to start using a lot of things on the back of your formula sheet. On the back of your formula sheet is the average Earth-Moon distance. That is center to center. Same with the average Earth-Sun distance. Those are all center to center distances. Okay, so I have what R is. Okay, and what is it? It's 3.5, right? 3.85 times 10 to the 8 meters, center to center. Okay. On the left side of that equation, I got mass of the Earth and mass of the moon. What mass am I putting on the other side? What mass usually goes in there? the mass that's doing what? Moving. The mass that's moving in a circle. Okay, which mass is moving in a circle? The moon. The moon's mass ends up on both sides because it's the thing that is going around and around in a circle. So what's going to happen to the mass of the moon? It's going to cancel out. Okay, so mass of the moon is going to be on both sides. I'm trying to figure out how fast the moon is moving in its orbit. So I need to isolate V. All right, so that means I'm going to multiply both sides by r. What is that going to do with the squared? All right, it's going to get rid of that and that, so those are going to cancel. Okay, we already said the mass of the moon is going to cancel, so that's out. What do I need to do to both sides? Square root. Okay, so when I'm plugging in my numbers here, I'm going to have 6.67 times 10 to the minus 11 times the mass of the Earth, also on the back of your formula sheet, 5.98 times 10 to the 24 kilograms, okay, divided by 3.85 times 10 to the 8, no longer squared. Okay. Does this get a little crazy for calculator entry? It is in this unit where showing your work is so absolutely crucial because it's so easy to mess up the calculator entry. Okay, please make sure you always show your work in case you mess up a number. All right, so if I'm putting this into my calculator, I've got two options. I can do it one piece at a time, or I can try and put it all in with a whole bunch of brackets. Whichever you feel more comfortable with is fine with me. All right, so if I'm trying to put this all in with the right number of brackets, okay, so there's my universal gravitational constant times the mass of the Earth. Okay, yep. Is that fast? That's 1 kilometer per second. Okay. It seems fast, but when you're talking about way out where the moon is, it's really not. Okay. You know, if you were near the Earth's surface, at that speed, you'd be going 3 times the speed of sound. But okay, out at that distance, it's not really so fast. The further away you go, faster or slower? Slower. Yeah. Okay. The further away you go, the slower you need to go to stay in orbit. Okay. It's very fast, close to the Earth's surface, about 8 kilometers per second. Okay, if you're close to the Earth's surface. That's why things can burn up when they fall out of orbit. They're moving very fast. Okay? And if they go through the atmosphere at that speed, they burn up. Okay, everyone all right with the math we did there? Okay, that is the basis for all satellite motion. Any satellite stays in orbit because gravity acts as a centripetal force. Okay. All right, now, knowing that, and okay, the radius of the moon's orbit, could I calculate how long it takes the moon to orbit the Earth? Yeah, definitely could, right? We just calculated how fast it's going, so we've got V. We know the radius of the circle, the orbit that it has, and I'm looking for how long it takes to make one orbit. Right? What formula am I going to use here? Two pi r over t. Yeah. Okay, I just got to swap v and t here. Okay, so we're looking at 2 times pi times 3.85 times 10 to the 8 over 1.012 times 10 to the, we have 3 there, right? Okay, so 2 pi times Okay, that number is in seconds, okay? Because we just divided meters here, okay? So we've got that number in seconds, so if we divide that by 3,600, okay, that's hours. Just about 28 days. Oh, because we calculated it, it was our speed. Oh, sorry, it was 1,017. I typed in the wrong number. Yeah, it should have been 1,017. So let's do that again, but we'll use the right number. That number. Close, right? Just about 28 days. Okay. Everybody all right with that?
Thanks so much.
Yep. Okay, so these are the kind of things that are going to come up with universal gravitation questions, okay? What we need to understand about gravity is just those relationships. The formula is easy, okay? But we need to understand that as mass increases, gravity increases. As radius increases, gravity decreases exponentially, okay? All right. If we want to go to other places in the solar system, what do we often do with our spacecraft? We slingshot them, okay? The gravity slingshot. If you've seen The Martian, okay, they use the gravity slingshot, right? What's his name? Childish Gambino there, the guy that he figures out, right, that if he brings the Hermes back and uses the Earth as a slingshot, he can get it back to Mars way earlier, okay? So we use that because the closer we get to something, the more gravity will pull and the more it will accelerate it. And then all we have to do is just use a little bit of fuel to change our trajectory so we don't actually fall in, and we gain speed basically for free. Yeah, way more free than we would if we actually just tried to use fuel. Okay, trying to just use fuel to accelerate something uses a lot of fuel, right? So when we're sending spacecraft to other places, okay, we just send them to other places first. Okay, so for example, okay, you can see some of these lines here that are headed out towards the outer planets. Okay, when they're launched from Earth, okay, so for like the Voyager spacecraft, they went to Jupiter first. Okay, and they, Jupiter was an important destination. They took pictures, but they used Jupiter as a gravity slingshot. Okay, and then they used that to fling them towards Saturn, and then they used Saturn to fling them towards Uranus, which, by the way, is how you pronounce it. It's not Uranus. That's something else entirely. Okay, Uranus is the way you pronounce that planet. Okay, and then they slingshotted from there to Neptune. Okay, and then the Voyager spacecraft, that was as far as they went. Okay, for New Horizons that ended up going past Pluto and some of those Kuiper Belt objects. Okay, well, on here it's not that far out. It was only here, okay, at that time, but it used the outer planets as well. Made a stop by Jupiter. Okay, we send things generally to other places to use gravity as an assist. Okay, now, is sending things to other planets difficult? Quite difficult. Okay, I mean, there are a lot of failures in space travel. Okay. If you look at the color coding on this diagram, okay, the bright colored lines are the successes. The darker colored lines are the failures. Right? So if you look at even something as simple as going to the moon, right, are there a lot of dark colored lines in here? Right? Apollo 13 would be a dark line. Okay? That one didn't land on the moon like it was supposed to. That would be a failure. Right? Look at Mars. There's like almost as many dark lines as there are light lines. Okay. What makes landing on Mars so tricky? Sorry, I'm not understanding what the...
Oh, it goes faster, so it's harder to...
Okay, yes. It does have to do with the initial speed coming in. Okay, what do we generally use to slow things down?
Force.
Okay, I mean in terms of if I want to land on Mars, what am I going to use to slow me down? Fuel a little bit. Parachutes, yeah. I'm gonna use air resistance. What is there not a lot of on Mars? Yeah, not a lot of air on Mars. So it's really tricky to try and land something on Mars because we can't do what we do on Earth, which is just let the atmosphere slow it down. Right? So they've devised all kinds of different ways to land things on Mars in order to understand that we can't just use air braking because there's not as much air. Do parachutes work? Sure they do. Okay? But only to an extent when you don't have nearly as much air. Right? The latest thing that we're using to land stuff on Mars is actually what they call the sky crane. Okay, so the Perseverance and Curiosity rovers used this. They had parachutes, and then as they got close to the Earth's surface, there's a ring of rocket engines around the probe. Okay? And they would fire and lower the probe. While they're firing, a crane, a cable, lowers the probe down towards the ground. Right? And then at the last minute, they cut the cable. Right? The probe falls the last 10 meters down to the ground. And once that cable is cut, the rocket ring just goes flying off because now there's no weight on it. It just flies off and crashes somewhere. Okay? We don't want to lower the probe all the way to the ground under the rockets because they'll kick up a bunch of rocks and dirt and stuff and damage the probe. That's why we actually let it fall the last 10 meters. Is 10 meters a long way to drop something? On Earth it is. On Mars, it's only like dropping it 3 meters. Gravity on Mars is less because Mars is smaller. Yeah. Okay? All comes back to that. These are all things that all those mission planners have to think of. Okay? They've got to think of those gravity calculations. They've got to know how close they're getting, what the acceleration is going to be, what the forces are going to be. It's why we give rocket science such respect. Okay? There's a lot of stuff that goes into it.
Could a slingshot with the sun, like, could we get close enough that it's worthwhile compared to, like, to get faster
Yes.
compared to other planets?
Yes. You can't get super close or you'll fry. But yeah, you could. Yeah, you absolutely could. Okay, so yeah, going to Mars, that's tricky. Okay, getting to land successfully, most of the problem is that you end up being a crater because you're going too fast. Okay? The other problem is also that you can't pilot anything to the surface. Because where are we? We're 1 light hour away. Any signal we send takes too long to get there. I can't just be sitting in mission control with a joystick, okay, and piloting something to the ground. It takes forever for my signals to get there. If I was relying on that, it would be a smoking crater every single time because of the delay. So everything has to be landed by computer. And those don't always get it right. Sometimes they crash. All right. So what about Venus? Look at Venus. Look at all these ones. Okay, it's a whole bunch of. What's the challenge landing on Venus? It's the opposite. Okay? Mars has an atmosphere 1% as thick as Earth's. Venus has the opposite problem. The atmospheric pressure is 100 times what it is on Earth, on Venus. So you're going through a thick atmosphere instead. Right? So thick that, I mean, yeah, you got the burning up problem, but you also have the completely crushed by the pressure problem. On the surface of Mars, the atmospheric pressure is so strong that it's stronger than under the deepest part of the ocean on Earth. That's how much the atmosphere weighs. Okay? So building a spacecraft that isn't crushed like a tin can on the way down is difficult. Ask the Russians. Okay? They had a very big problem with this back in the 80s when they were trying, well, 70s and 80s, when they were trying to land probes on Venus. Okay? They had a lot of failures because they were simply crushed kilometers, hundreds of kilometers from the surface. Okay? And then they had some quite comical problems after that. They actually got a few probes to land on the surface. Okay? So the first probe that got to the surface, what they wanted to get out of that was pictures, and a sampling arm was going to go down and sample the surface, okay, and just send back some readings. So they had, the probe was shaped like, kind of like my fist here, okay? The camera was right here, and the arm was right below, right? Now, you have to have a lens cap. on the camera to protect it going through a thick atmosphere like that. So the thing gets to the bottom, the lens cap gets popped off by the little explosive charges, okay? And then the sample arm goes down and samples the lens cap. I mean, come on. You put the camera right over top of the sampling arm, and then you pop the lens cap off. Where did you think it was going to go? Okay? I mean, somebody ended up in Siberia over that one, I'm sure. Okay? Because the next one obviously had them offset several degrees so that wouldn't occur. Okay? But they had a lot of issues landing there. But once they got it figured out, they landed there consistently. Okay? Got lots of pictures and things like that. Okay? But it's tricky. Okay? It's tricky to land somewhere else because gravity is different. There's delays and all that stuff has to be accounted for. Okay, we already did that. So slow. Okay, I would like you guys to try 1 and 2 there. They both involve using Newton's universal law of gravitation. Okay? Okay, so on number 2, okay, my givens for number 2 are that they tell me the force of gravity is 61 newtons. All right. They also tell me that the separation distance, center to center iceberg to the center of the Titanic, is 100 meters. Okay, and that the mass of the Titanic is 4.6 times 10 to the 7 kilograms. All right, we're looking for the mass of the iceberg. All right, so Fg is going to equal big G times the mass of the Titanic times the mass of the iceberg divided by r squared. So I'm going to multiply both sides by r squared and then divide both sides by big G times the mass of the Titanic. Okay, that'll leave me with the mass of the iceberg. So 100 squared times 61 and then divided by 6.67 times 10 to the minus 11 times 4.6 times 10 to the 7. Okay, when I do that, I should end up with 2.0 times 10 to the 8 kilograms. So the iceberg was considerably larger than the Titanic was. Okay? Is this why the Titanic hit the iceberg? Because they were gravitationally attracted to each other? No. A 61 Newton force is not moving either of those objects. Okay? Not at all. Okay? It's because navigators were, making drinky, okay, and weren't at their stations when the iceberg came in. Okay? Everybody with me on that? Okay, in the first question, is that an incredibly small force of gravity? Would you even notice that? No, you're not going to feel pulled together sitting on a park bench. Okay. Okay. Okay, want to walk through this one, okay? Because it's kind of it's a weird question in that it gives us some numbers but not a lot of numbers. Okay, so in this question they tell us that object A exerts 1.3 times 10 to the minus 10 newtons of gravitational force on object B. So they tell me the force of gravity. Okay? 1.3 times 10 to the minus 10 newtons. Okay? Then they say, without any other numbers, determine the gravitational force if the separation distance is doubled, mass A is increased by 6 times, and mass B is halved. How in the heck am I supposed to figure that out without any real numbers? The answer is with ratios and understanding the relationships. Okay? In this first situation, if I just say that the force of gravity was big G times 1 over 1 squared. They just make everything, this is my first situation, everything's a 1. Okay? It obviously isn't, or I wouldn't get that number, but I'm going to say that it was. In the second situation, so this is force of gravity 1. Okay? In the second situation, I've got big G, but now mass 1 is 6 times heavier. Okay? and mass B is half, and the separation distance is double. Okay, if I put that in, even without the big G there, okay, will I get how many times bigger or smaller the second situation is than the first? Yes. As long as I have the understanding that the relationship is as mass gets bigger, force gets bigger. As radius gets bigger, force gets exponentially smaller. As long as I know the ratios, I can just plug the ratios in. Okay? So I can just say, well, it's going to be 3 over 4. Right? 6 times 0.5 is 3. 2 squared is 4. Okay. So in the second situation, the force of gravity will be 3/4 of what it was in the first one. Does that tell us pretty unequivocally that radius has a bigger effect than mass? Right? I've got 3 times more mass in the second situation. But when I double the radius, it quarters that force. Agreed? Okay. That's all that question is really asking is, do you understand that mass has less of an effect than radius? Okay? And can you put in ratios to figure it out? Hudson, you're giving it a weird look. Where did I lose you?
No. Then would you times the 3/4 by?
By that value, yeah, and then I would have the actual number. Okay, here's a very common question that I would even put on a unit exam. It's a gravitation question, but it's also a Newton's second law, net force kind of question. All right, so not using these numbers, use the ones on your sheet. So 5.98, 7.36, that's fine, 3.85 there. Okay. I want you to calculate when the Earth, Moon, and Sun are in this orientation. Okay, so this is a lunar eclipse. Okay, I want you to calculate the net gravitational force acting on the Earth in this situation. Okay? Find the net force acting on the Earth in this situation. Okay, to get to that, think about this. How many forces are acting on the Earth? And can you calculate that? Okay, in this question, how many forces are acting on the Earth? 2. Okay, there's the mutual attractive force between the Earth and the Sun. And there's the mutual attractive force between the Earth and the Moon. The mutual attractive force here between the Moon and the Earth is going to pull the Earth this way. Okay? The mutual attractive force between the Sun and the Earth is going to pull the Earth towards the Sun. All right? Can I calculate both of those numbers? Absolutely. Okay? It's 2 calculations of the force of gravity. So between the Sun and the Earth, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 1.99 times 10 to the 30, the mass of the Sun and the mass of the Earth. And then I'm going to divide that by the separation distance between the Earth and the Sun squared. Okay? And then I've got to do the same calculation between the Moon and the Earth. All right? So 6.67 times 10 to the minus 11, 5.98 times 10 to the 24, because we need the Earth in there. Then we need the Moon, 7.36 times 10 to the 22. Okay? And divide that by the Earth-Moon distance, 3.85 times 10 to the 8 squared. All right? Now, when we do that, what we find is this ends up being like 3.53 or 3.54 times 10 to the 22? 3.52, okay. Yeah, 3.52 times 10 to the 22 newtons towards the Sun. Okay, and this one ends up being like 9 point something times 10 to the 20, right? 1.98. 1.98 times 10 to the 20 newtons. Okay, so is the force between the moon and the earth a lot less than the force between the earth and the sun? And that's why the earth orbits the sun and not the moon. Okay, it's far more attracted to the sun because the sun is so much bigger. Okay, it's way further away, but it's also a lot bigger. All right, so if I want to find the net force, well, net force is just the vector sum of all forces. Force of gravity between the sun and the earth minus the force of gravity between the moon and the earth. Okay, and what we're going to find is this is like 3.51 or 3.50 times 10 to the 22 newtons towards the sun. Okay, it's hugely towards the sun. But there is some force on the earth from the moon. So does that mean that the earth would move in a perfect circle around the sun? It doesn't. Okay? It wobbles back and forth all the time as it orbits the sun due to the moon and other things that might go by. Okay? Everybody all right with that idea? I'm going to tell you right now that I almost always ask a question like that on both the assignment on gravitation and the unit exam, and probably a quiz on gravitation as well. Okay? It's net force, that's unit 2, but it's also gravitation, that's this unit. Okay? All right. If I was going to do number 1, do I need to do any calculating other than what I already did? Okay? The forces are still the same, right? It's still the force of gravity between the sun and the earth and the force of gravity between the moon and the earth. But now what am I doing with those forces? I'm adding them. Okay? If the moon is in between the moon and the sun, or sorry, the earth and the sun, then it's going to pull it towards the sun as well. I'd be adding those forces. Okay? You could get any one of those situations. Or what about when it's out to the right? How does that change things? I mean, when we were doing these other ones, did we just go one force and one force? Would I have to do that for this?
Tail to head.
Yeah, tail to head. Okay, I'm going to have the force of gravity, okay, between the earth and the sun, and then the force of gravity between the moon and the earth. It's so small by comparison, but it does create a small deflection, right? Just don't, my message here is don't forget things from unit 2. Okay, they still apply here. Vector sum of all forces, all of that kind of stuff. Okay. All right. Tomorrow we are going to go over satellite motion and maybe a little bit about a guy named Kepler. And then on Wednesday, Mr. Van Erb will be interviewing, and you guys are going to work on some stuff to do with field strength and problem solving and stuff like that. Okay, and then Thursday we'll probably finish up the gravitation stuff. Okay, this Friday's quiz will be on vertical circular motion, and only vertical circular motion. So I believe those are practice quizzes 3 and 4. I'll double check, but I'm pretty sure that they're 3 and 4. Okay, good job today, guys.